Hello students, let us start with our third unit next topic which is known as on Risc instruction set computer. So in today's class we will be going to discuss about the Risc and Cisc instruction set computer. What do you mean by Risc? Risc is nothing but a reduced instruction set computer, whereas Cisc is nothing but your complex instruction set computer. Let us cover the characteristics of Risc and Cisc. If you're going to specify the name in the name itself only, you can understand that what actually you mean by this computer system. Complex instruction set computer is nothing but in this computer we are going to have the complex instructions, whereas in the reduced instruction set computer we are going to have only a few direct instructions that can be used for your programming. Let us come with the characteristics of your Cisc architecture. In the Cisc architecture, a large number of instructions, typically from 100 to 250 instructions, you are going to have in our Cisc architecture. Some instructions that perform the specialized task and are free used and are used infrequently. A large variety of addressing modes, typically from 5 to 20 different addressing modes you are going to have. And apart from this one, you are going to have the variable length instruction formats. Instruction format will be of variable length. Next is nothing but your instruction that manipulates the operands in memory. Okay, this instruction can manipulate the operands in memory. That will be there in the complex Cisc instruction architecture. This is related with your Risc instruction set, Cisc instruction set. Next, coming to the Risc in instruction set computer, the characteristics are nothing but here you are going to have very few instructions. You're not going to have many instructions, you are going to have few instructions. And in this we are going to have very few addressing modes, and the memory access limited to load and store instructions. You can able to access the memory by using only two instructions, load and store instructions. All the operations done within the registers of the CPU. All the operations you are going to done by using the registers of your CPU. Whereas in the Cisc we are used to always all the instruction can manipulate by using the memory. So, the fixed length easily decoded instruction formats. You are going to have fixed length instruction formats which can easily decode it. And you are going to have single cycle instruction execution. You're going to have single cycle instruction execution, a hardware rather than the microprogrammed control unit. You're going to have the hardwired control unit, not the microprogrammed control unit. So these are the few characteristics. Based on these characteristics, you can write down the differences between Risc and Cisc, and this there will be chances of asking from this unit the differences between the Risc and Cisc architecture. What are the other characteristics of Risc architecture is nothing but a relatively large number of registers in the processor unit. You are going to have a very large number of registers in the processor unit. Used to overlap the register windows to speed up the procedure call and return. So we are using an overlap register windows. Overlap register window, what it is, we'll see in after a few seconds. And if it is going to have the efficient instruction pipeline. Compiler supports for efficient translation of high level language programs into a machine language programs. Okay, now what is overlap register windows? In this overlap register windows, if I'm going to see here, for example, I'm having suppose I'm having procedure A, procedure B, procedure C, and procedure D. That is nothing but I'm going to have a procedures. This will be there. Okay. Now, if I'm going to see that there are global register from R0 to R9, which has been accessed by all these particular procedures. Okay. Now, we will be going to see, if you are going to see here, some registers, like for example procedure A, if I am going to consider, in procedure A, R10 to R15 registers are common for your procedure A as well as procedure D. So for procedure A and D, these registers are common. So this particular two register memory locations will be overlapped with each other for procedure A and procedure D. Okay, now if you are going to see here, registers R31 to R26 is common for procedure B as well as procedure A. So this particular area will be common for A and B to access this particular area, memory locations, is memory, that is the register window. So this will be acting as an overlapped register window. The same thing happens for your register R14 to R27, which is in yellow shade. If you are going to see, this is common for procedure C and procedure B. So this will be common area which will be there, and this common area is being utilized by procedure C as well as procedure B also. So that is why this is known as an overlapped register window. Okay, now what is the advantage of this overlap register window? The time consuming operations during the procedure call, saving and restoring the registers, passing of the parameters and results, so that will be very time consuming. Overlap register windows provides the passage of parameters and avoid the need for saving and restoring the register values by hardware. Okay, so that is nothing but it is going to avoid the time. Okay, the time consumption will be going to avoid by using this overlapped register window. If I'm using separate procedure, procedure A separate memory location, procedure B separate memory location, C separate, D separate, then each and every time I need to save, restore the registers value. Passing the parameters from one procedure to another procedure will also be a very big headache. So by using this overlapped register window technique, I can provide a passing of the parameters and avoid the need of saving and restoring of the register values. Okay, so that is the main advantage of your overlapped register window. Okay, the same thing what I have discussed, they have discussed here. Okay, R0 to R9 registers are global registers. Total 74 registers are there. We are using four windows, window A, window B, window C, that window D, which is nothing but your procedure A, procedure B, procedure C, and procedure D. Okay, each register, if you are going to have, I'm going to have 10 local registers plus two sets of 6 registers common to adjacent windows. We are using two sets of 6 registers. So that is nothing but your down procedure common and up procedure common. Okay, this is done with your Risc and Cisc architecture. Okay, next let us come with the next topic, which is known as the pipelining concept. Next comes with your pipelining and vector processing. What do you mean by pipelining and vector processing? We will be going to see in today's class. Let us come with the first parallel processing. What actually you mean by parallel processing? I am executing parallelly many programs together or many instructions together is known as a parallel processing. Okay, simultaneous data processing task for the purpose of increasing the computational speed. To increase the computational speed, we will be using a simultaneous data processing. Performs the concurrent data processing to achieve the faster execution time. Okay, to execute the faster execution time, we will always go with the parallel processing. So multiple functional units. Okay, separate execution unit into 8 functional units operating in parallel. So what we'll do, we'll be going to divide this into multiple functional unit. The computer architectural classification, if I'm going to see here, data instruction stream, pipeline, okay, serial versus parallel processing, parallelism and pipelining. Okay, so these are nothing but a different computer architecture classifications. We'll be going to see one by one. Now if you're going to see here this particular example block diagram over here, I'm using a processor register. This processor register is been given to the sub-functional block units. One is nothing but your adder subtractor unit. Second is nothing but your integrator and multiply unit. Next is logic unit, shift unit, incremental unit, floating point add and subtract unit, floating point multiplication subtract multiplication unit, and the floating point division unit. So we are dividing it into different functional units. Okay, next comes with your line classification. In this line classification we are going to classify it into different types. First one is something but your SISD. SISD is nothing but a single instruction, single data stream. You are going to have single instruction and you are going to have single data stream. For practical purpose, only one processor is useful. So here what you are going to have, you are going to have here control unit, you are going to have instruction stream, program unit, and you are going to have the data stream from the memory. Okay, from the memory you are going to take the data stream. Later on it has been given as an instruction stream into the control unit. So this is nothing but a single instruction, single data stream. I am going to have only single data stream. Next one is what? Single instruction and multiple data stream. Single instruction and multiple data stream is nothing but a vector or array operations. We are going to have vector or array operations. One vector operation includes many operations on a data stream. Examples are nothing but Cray 1, IAC 4th is nothing but examples of this system. Now how it is been executing here? I am having a control unit. Next, I am dividing into program units. I am going to have different program units, and each program unit will be having a different shared memory. So I am again dividing my memory into subunits. Okay, so one subunit of memory will be accessed by one particular program unit. Another subunit of memory will be accessed by the another program unit. Okay, so on you are going to have multiple program units and multiple shared memories. So this is nothing but a single instruction stream. I am going to have single instruction stream, whereas the data streams I am going to have multiple data streams which is connected to different program units. Next one is what? Multiple instructions and single data stream. I'm having a single data stream but multiple instructions. What I'm doing, I'm having a different control unit blocks. Each block will be going to have different instruction stream. Okay, now this instruction stream is connected to the program unit. Okay, but as we have said here in this, I am going to have only single data stream. Single data stream means I am going to have single data shared memory. Okay, from that only we will be going to access the data stream, that is nothing but your data stream bottleneck. It is very that is nothing but at once I cannot able to give the data to multiple instructions at the same time. Next is what? MEMD. MEMD is nothing but multiple instructions and multiple data streams. Here I am having multiple instructions and multiple data streams. So it is acting as a multi-processor system. So I am having a different control units. Each control unit will be having its own instruction stream, and later on it has been given to the program unit. From the program unit will be getting the different data from the shared memory. Okay, let us concentrate on our main concept over here: pipelining processes, arithmetic pipelining and instruction pipelining, vector processing and array processing. Okay, so if I'm going with an vector processing, I'm going to have adder and multiplier pipelining. If you're going with an array processing, we are going to have array processor, attached array processor, and SIMD array processor I'm going to have. Let us start with our main concept, pipelining. What actually you mean by pipelining? A pipelining is nothing but decomposing a sequential process into a sub-operation. I am going to divide my complete process into subdivisions, sub-operations. Each sub-process is executed in a special dedicated segment concurrently. That means that each sub-process will be executed in a special dedicated segment concurrently. Okay, let us see one example you can understand over here. Pipelining example, multiply and add operation. Okay, now if I am going to have called AI into BI plus CI, The I is nothing but 1, 2, 3 till 7. So 3 sub operation segments I am going to have. R1 register will be going to loaded with AI value. R2 will be loaded with BI value, that is input AI and BI. Second sub operation is what, R3 is loaded with R1 into R2, that is nothing but your AI into BI we are performing, and at the same time I am moving my CI value into the R4. Next, later on R5 is equal to R3 plus R4 and we are going to perform. Okay, so in any of these particular sub operations we are not overlapping any or misleading our data. So what happens here? Now let us take here one example, the same example over here. In the clock, suppose first clock pulse, what happens? I am moving the data called A1 and B1. In the second clock pulse, what happens? I am moving the data called A2 and B2 in the R1 and R2 register. At the same time, my previous A1 and B1 data will be multiplied with and result will be stored in the R3, and at the same time C1 value will be stored in the R4 register. In the third clock pulse, what happens? I am moving the data called A3 and B3 in your R1 and R2, and the previous value A2 and B2 will be multiplied and the result will be stored in the R3 register, and at the same time C2 value will be moved into the R4 register, and at the same time we are going to perform third operation, that is nothing but your R3 plus R4, and the result will be stored in the R5. Okay, so this will be repeated again and again. Now if you see here, we are for performing total 7 operations, that is nothing but 1, 2, 3, 4, 5, 6 and 7. To perform these 7 operations we require total how many clock pulses here? Totally 9 clock pulses. Okay, but if I'm going to see here the sub operations, if I'm going to see, I'm have for each I operation we require 3 E sub operations. So totally for 7 means 7 3s are 31. We require 21 clock pulses to perform this particular operation, but we are reducing it to 9 clock pulses. By this the speed of execution is been increasing. That is known as a pipelining concept. That is nothing but each and every operation whichever we are performing, we are dividing it into sub operations in such a way that these sub operations will not be going to mislead the data. That you need to keep it in mind. Okay, so this is nothing but a pipelining concept. Now let us consider with this pipelining. Generally whenever we go with the pipelining concept, now we go with the pipelining concept. General consideration we need to go 4 segment pipelining concept. S is nothing but your combination circuit for sub operation. R is nothing but your registers, intermediate results between the segments we are going to store. So what happens here? I'm having sub operations, that is nothing but a combination circuits S1, S2, S3, S4, so on. Okay, and between S1 and S2 of sub operation I'm placing one register called R1. From S2 and S3 sub operation we are placing a register called R2. Next we are placing an R3 between S3 and S4, so on you are going to do, and each register will be given a clock pulse. Now you are going to give the input to the S1, that is nothing but your combination circuit sub operation S1. Okay, same way you will be giving the data to S2 also based upon the requirement of your sub operations. Okay, now for this same thing, if I'm going to draw the timing diagram, space time diagram, if I'm going to see in the first clock pulse what happens, your states T1, T2, T3, T4, T5 and T6 will be going to execute. In the second clock pulse what happens, at the second clock pulse you are going to again execute T1, T2, T3 till T6. In the third clock pulse, yes, that is nothing but the third as clock pulse, third segment you are going to execute T1, T2, T3. That the fourth you are going to have the this one. So now if you are going to see here, your first segment will be executed at first clock pulse, and your second segment will be will start executing at the second clock pulse, and the third segment will be start executing at the third clock pulse, and the fourth segment will be start executing at the fourth clock pulse. So that is nothing but your T1 to T6 are nothing but a different task. That is nothing but your sub operations. Okay. Now let us see that how the speed is been calculated for your non-pipelining and a pipelining concept. If I'm going to go with a non-pipelining or pipelining concept, well, how much time it is taking, and how you are increasing your speed of operation. With pipelining, K segment pipeline with the clock pulse time as TP to execute n task. Without pipeline, each task takes Tn seconds. So what happens here? S is equal to n into Tn by K plus n minus 1 into Tp. So that is nothing but how many tasks, how many n is nothing but your task. How many tasks are there? 6 tasks are there. 6 into 6 Tn divided by 4 plus, that is nothing but your K value. What is your K value? Is nothing but your segments. How many segments? 4 segments plus n value 6 minus 1 into Tp. So you will be getting at this, if you are going to calculate, you are going to get it as 4. Okay, so n is nothing but your task number, and Tn is nothing but your time to complete each task in non-pipeline. Okay, now clock cycle time, which is nothing but your 1 clock pulse, and K is nothing but your segment number. So you are increasing 4 times your speed of operation. What is instruction pipeline? Instruction pipeline is nothing but your instruction. Based upon my instruction cycle execution, we are having an instruction pipeline. So in the instruction cycle, what are the different steps we are going to have? Fetching first is nothing but your fetching the fetch cycle, which is nothing but your fetching the instruction from the memory. Second is nothing but your decode the instruction. Third is nothing but your calculate the effective address. Fourth is nothing but your fetching the operands from the memory, and the fifth one is nothing but your execution of the instruction, and the sixth is nothing but your store the results in the proper place. Okay, now same thing happens. Same thing if you are going to see, this is your flow chart. How this instruction pipeline is been executed. If you are going to concentrate on this flow chart, first fetch the instruction from the memory. We are going to fetch the instruction. In the second, decode the instruction and calculate the effective address. In the third one, whether there is a branch operation or not. If it is no branch operation, fetch the operand from the memory and execute the instruction. Okay, after execution of instruction, is there any interrupt or not? If there is no interrupt, it returns back to your fetch the instruction from the memory. If there is an interrupt handle will be done and update the PC. Next, empty the pipeline and return back to your main program. If there is a branch instruction, then I am going to change my power program counter address value. Then I am going to empty the pipe and I am going to return back to your main program. Let us take one small example over here. 4 segment instruction. I am taking 4 segment instruction pipeline. In this I am dividing into four parts. I am dividing my instruction cycle into 4 parts. First is nothing but your F5, which is nothing but your instruction fetch. DA is nothing but your decode the instruction and calculate the effective address. F4 is nothing but your operand fetching. EX is nothing but your execution. So the timing of instruction pipeline: instruction, 3 instructions of branch. Okay, now let us, if you are going to see the no branch and branch instruction, how it is going to differ. Now what happens first is, at the first step, what happens in the first, you are going to have, you will be executing first instruction F5, that is nothing but your instruction fetching. Next, decode. When in the second clock pulse, your first instruction will be decode the instruction and if you calculate the effective address, and at the same time you are going to fetching the next instruction, second instruction. Next, in the third clock pulse, The first instruction you are going to do the operand fetch. Second instruction will be a decode and decode the instruction and calculate the effective address. And in the third clock pulse, you are going to you are going to fetch the instruction. Okay. In the next fourth clock pulse, first instruction will be executed. Second instruction will be operand fetch. Third instruction will be your decoder instruction and calculate the effective address. And the fourth instruction will be your fetching of an instruction. Okay. Now, if it is no branch, the for all the clock pulses it will be go so on. It will be repeating. Whereas if there is a branch, if suppose there is a branch occurs at F1, that is nothing but at your fourth instruction there is a branch instruction. What happens is nothing but your I'm sorry. The third instruction is your branch instruction. Then execution after the branch instruction only, your fourth instruction will be fetched. So branch during the branch instruction format, first the third instruction will be executed completely till sixth clock pulse. Once this the instruction has been executed, then you are going to go with the fourth instruction, that is nothing but your branching instructions. Okay, so there again you are going to execute same thing. You are going to have F5 DA FI combination, next FO DA FI combination, next execute operand fetch, next is nothing but your decode the instruction, next is nothing but your fetching the instruction. So it will be repeated. If there is only if there occurs, if any instruction occurs branch instruction, then branch instruction will be executed completely, then only it will be shifting to the branched instruction. Okay, the next instruction will not be fetched until and unless the branch instruction is executed. Okay, the main three major difficulties you are going to find it in the pipelining conflicts. One is nothing but your resource conflicts, memory access by two segments at the same time. Okay, if at the same time if both the segments are going to access the memory, then that will be a conflict. That is will be a conflict. Next is what data dependency. When an instruction depends on the result of a previous instruction, but this result is not yet available, then it is known as a data dependency. And the next one is something but your branch difficulties. Branch and other instructions that can change the value of PCE. Okay, so these three are nothing but your three major difficulties you are going to you are going to find it whenever you are going with a pipelining conflict. Pipelining concept. What is data dependency? Data dependency is nothing but your based upon my previous execution result only, I am going to decide my next instruction to be executed. Like for example, in suppose if I'm considering the branch instruction. In the branch instruction, what happens? I'll be checking some condition. So the condition that is the carry generated or not. This carries will be generated only after execution of my previous instruction completely. So I cannot execute my third instruction pipelining. Okay, so there we're going to have the data dependency. Okay, so in the hardware part, if I'm going to see the data dependency, then hardware interlock, previous instruction, hardware delay, operand or forwarding the previous instruction, software delay loaded previous instruction. So the much required. Coming to the Risc pipelining concept, an instruction pipeline and single cycle instruction execution and the compiler support. Three segment instruction pipeline, if I'm going to see, I'm having a three sub operation instruction cycle. I is nothing but instruction fetch, IA is nothing but instruction decode and ALU operation. E is nothing but transfer the output of ALU to the register or memory or PC. Okay. Now, what happens here? If I'm going to see here how the conflict is going to occur, we are going to see. Now in the first clock pulse we are going to load the register R1. Second, so what are the instructions? First let's see. First loading an instruction, loading the register R1. Second loading the register R2. Next performing the addition between R1 and R2 and store the result in the R3. So what I need to do in the first case of the first clock pulse, your first instruction load R1 will be, instruction will be fetched I. In the second clock pulse, first instruction will be under instruction decode and ALU operation, and the second instruction will be fetched. In the third clock pulse, what happens? Your first instruction will be executed. Second instruction will be under a, that is nothing but your instruction decode and ALU operation, and the third instruction will be fetched. Now what happens in the next clock pulse, fourth clock pulse? Here the second instruction will be executed and the third instruction will be in the decoder and ALU operation. This brings to the conflict. Why? Because this second instruction should be executed before your instruction is decoded and ALU operation is performed, because I want my that particular R2 register value, whereas in your the R2 is not at all loaded. It is loaded at that particular same time. So that is why this will be acting as a conflict. Pipelining timing with a data conflict. Okay, now pipelining timings with delayed call load. If I'm going to see what happens here, what I'll be doing here, I'll be going to add a no operation statement here. Whenever I'm adding a no operation statement, what happens here? Nothing will be done, but your 3 cycles will be going to execute it. So due to this one, what happens? My third instruction will be getting some time to get the data. Okay, so now if I'm using a delay load, what happens here? At the third instruction, instead of doing add R1 plus R2, I'm performing no operation. Next, fourth instruction will be my add R1 plus R2. Now in the fourth clock pulse, what happens? Your R2, that is nothing but your load R2 register value will be loaded in the R2 register, so it will be executed. So your next is what happens here? No operation instruction will be decoded and ALU operation, that is not required at all, and your add R1 plus R2 instruction is fetched. In the next fifth clock pulse, when your add R1 and R2 are under instruction decode and ALU operation, already your register R1 and R2 both are reloaded with your values. So it performs the ALU operation and then it will be going to execute. So by this we are going to reduce this conflict. So we are going to produce a delay load, that is something with your no operation load. We are going to add it in our instructions. Same thing with small example they have given with the no operation and with operation. Next comes to vector processing. Vector processing is nothing but based upon the science and engineering application, long range weather forecasting, petroleum exploration, seismic data analysis, medical diagnostics, aerodynamics, space flight simulation, artificial intelligence and expert system, mapping the human genome, image processing. In these applications we are going to use this vector processing. In this vector processing, why we are saying it is a vector processing is something more, we are going to have bunch of data, sequence of data. So this sequence of data to perform arithmetic operations on large arrays of numbers and conventional scalar. So let us take one submission language. Initialize I equal to 0, read A of I, B of I, store C of I equal to A of I plus B of I. Increment I plus 1, and if I is less than or equal to 100, go to 20. and continue. So this is nothing but your I value should be there from 1 to 0 to 99, that is total 100 readings I am going to process. So this is known as a vector operations. Vector processes are nothing but a single vector instruction, that is C equal to 1 is to 100, that is 1 down to 100, that is equal to A 1 down to 100 plus B 1 down to 100, single instruction, which is known as a vector operation. In the vector instruction format, I am going to have the operation code add my base address register source 1 A, base address register source 2 B, and base address register destination address register C. Next, what is my vector length? How many times I should go with that operation? That is something which is 100 times. So add A, comma B, comma C, comma 100. So this is nothing but a vector instruction format. So matrix multiplication also, if I am going to perform, then I always go with this type of vector operations. Pipelining for calculating an inner products. Okay. Floating point multiplier pipelines 4 segments. Floating point adder pipeline 4 segments we are going to have. Okay, now if I am going to see here, C is equal to A1 into B1 plus A2 into B2 plus B3 into B3, so on. So what I need to do, I need to first perform A1 into B1 so on till AK into BK. So what happens here, in the first clock pulse, what happens here, source A and source B are there. So you are going to have the multiplier pipeline. So continuously you are going to have the A1 into B1 so on till A3 into 3A4 into B4. Okay, and it is be given to the adder pipeline. Okay, and the result will be there. Next, after fourth the clock pulse, what happens in the same pipeline, I am going to have the next values, that is nothing but your A4 B4. Okay, so it has been moved into A3 B3, A2 B2, A1 B1. So that is nothing but your at the fourth clock pulse. In the first clock pulse, A1 and B1 will be there in the first segment of your multiplier pipeline. In the second clock pulse, what happens, A1 and B1 will be moved to here, and A2 and B2 will be coming into the multiplier pipeline. So both the values will be there. And next again the third clock pulse, A3 B3, A2 B2, A1 B1 you are going to have. In the fourth clock pulse, you are going to have it as a A4 B4, A3 B3, A2 B2, A1 B1. Okay, so you are going to have. What happens in the next one, in the eighth, after eighth clock pulse, what happens after eighth clock pulse, your A1 B1 all everything will be moved to the adder pipeline, and you are going to get the remaining next four values, that is nothing but your A5 B5 to A8 B8. Next, after 9th, 10th and 11th clock pulse, what happens, we are going to get the results called as A1 B1 plus A5 B5 plus A9 B9 plus A13 B13, so on you are going to get it. So what is memory interleaving? Memory interleaving is nothing but a simultaneous access to the memory from two or more sources using one memory bus system. So I am going to use only one memory bus system. We are from one memory bus system, we are going to access memory from two or more sources. So I am going to divide it into add or even an address memory access. Okay. So, supercomputers uses this vector instructions and pipelined floating point arithmetics. By this we are done with our third unit. In the next class we are going to start with our next unit. Thank you.